Okay, so I'm hoping third time is a charm with this problem, because my dog is just obsessed with things in the neighborhood. I think it's all the blowing leaves and the squirrels, and she's got to protect the home front, and etc. etc. So this is fall 2019, problem number 2, exam 3. And the first thing we're going to look at it and just eyeball it. Do we look like torsion, twisting, or does it look like axial deformations, things getting shorter and longer? And to me, it looks a lot like axial deformation. So we have this aluminum rod, and it's going to be supporting rigid bar ABCD. It's pin supported, so I have to remember there's a reaction there. We are pulling down like this. We are also decreasing the temperature in this rod, which is going to make it contract as well. Determine the stresses in the steel cable and the aluminum rod and the displacement of point A on the rigid bar, blah, blah, blah. So if I want to determine stresses, I know that we're normal stress. It's going to be P over A for each bar. And if I want to find a displacement, I know that displacement is change in length. It's going to be some sort of a PL over AE. Okay, so this is rigid. It's going to want to rotate, and I'm just going to go ahead and start putting all my information. So this is aluminum, and it has a length of, I just erased it, so now I can't really see it very well. I think it was 5 feet. Yeah, 5 feet, so that is 60 inches. Okay, it's aluminum, so it has an E of 10,600 KSI. It has an alpha, or coefficient of thermal expansion, of 12.8 times 10 to the negative 6 per degree Fahrenheit. So if we're looking at, we need to find stress. Okay, if I need to find that stress equals P over A, I need to find the area. So here is, okay, this looks a lot like the problem I just worked with torsion. And we just did a thin-walled problem, thin-walled in torsion. This is not in torsion, this is in compression. All I need is the cross-sectional area. So if the outside dimensions are 3 inches and I have a thickness of 1/8 of an inch and a thickness of 1/8 of an inch, then my total thickness when I look across of 3 inches is 1/4 inch. So I know the inside dimensions are 2.75. So I'm going to take an outside of a 3 by 3 minus an inside of 2.75 so that I can calculate the gray area that's remaining. Okay, so if I look at my area, okay, it is going to be 3 squared minus 2.75 squared, and I get an area of 1.4375 inches squared. So I can do my stress. I could do delta equals PL A E. I have everything right here. I have a steel cable. Okay, it has an original length of 36 inches. It has a modulus of 29,000 KSI. It has a cross-sectional area of 1 inch squared. And friends, we need to start looking at units, okay? How do I know this is an area? Because units are inch squared. Square is an area. If it was like a diameter or a radius, we would have units of inch. Okay, and this seems to be a huge issue with many of you is, I didn't say this is an area, but how did I know it was an area and not something else? Units. Area is inch squared or meter squared. Okay, and I don't need its thermal expansion because it's not heating up or cooling down. I guess I should put over here, this goes from 100 to 50. So we have a delta T of minus, where does that come from? A delta T of 50 minus 100, final minus initial. So I have a delta T of negative 50 degrees Fahrenheit. Okay, so I have everything kind of in one place. So I'm always going to start with equilibrium. Okay, equilibrium. That's my number one starting place every single time. And I'm going to just try to make some guesses as I'm looking at this. 25 kips pulling down, and I'm heating up, so it's getting shorter. If this is a rigid bar affixed it here at C, at pin at C, then chances are, as I'm pulling down here, it's going to want to rotate something like that. Okay? And if it's rotating something like this, this is actually a compression member, and this is a tension member. And I'm just going to go ahead and assume that as I'm kind of going through. So if this is a compression member, it is pushing back up. So a compression is pushing down on the member, pushing back up on the joint. So I have a force at B. I have CY and CX. Don't forget about those. If this is a tension member, okay, we're trying to pull up. This member is being stretched up. So we're pulling back down on the member, and I have that force at D. I have 4, 6, 2. So quickly, I have an unknown FB, an unknown CY, and an unknown FD. Okay, I have 3 unknowns in the Y direction. And if I look, I can sum forces in the Y direction, and I could take the moments about C if I wanted to. But that only solves for two forces. Okay, that only solves for 2 forces. I am still missing one. So I know that I'm also going to have to use my compatibility. Okay, so let's go ahead and set this up over here. I'm going to sum the moments about C, because right now I don't care about the force in C. I don't have to design that pin. And if I sum the moments about C, I'm going to have an issue with my pencil here. Always. Okay, I'm going to have a positive 25 times 8 minus FB times 6 minus FD times 4 equals 0. I'm going to divide through by 2. I just like smaller numbers. So I can bring my negatives over, leave the positive here, and I have 3FB plus 2FD equals 100. And I know because I'm having to use compatibility and I've got 2 unknowns, I'm going to have 2 equations. So I'm going to go ahead and just isolate FD. Okay, so I have 100 minus 3FB. And I'm going to divide through by that 2. So I get that FD is 50 minus, oh, nobody here to tell me you can't see, minus 3FB over 2. So now we have our relationship on equilibrium. And remember, I'm assuming this is in compression. I'm going to assume that that's, you know, for directions in terms of equilibrium, it's a negative moment. When I come over here and look at compatibility, I'm going to have to remember that I'm assuming it's in compression. So I'm assuming it's going to kind of rotate like this. I'm going to have a delta D, and I have C. We're rotating around that. I have delta A, and I have delta B. And when I look at this, these 2 are rotating down. That one's rotating up. I'm going to call up negative. It doesn't matter which way you want to do it. Okay? And I know this is 6, 2, and 4. So with compatibility, I can look at this big triangle, and I have delta A is 2, 6, 7, 8, as delta B is 2, 6, as negative delta D is to 4. Okay, because it's going the opposite direction. And when I know about deltas it's a function of force and temperature change. And we have force and temperature change on B, and we just have force on D. So I can go ahead and start simplifying, and I can say, well, let's just get rid of a 2 here. So I've got a 2 and a 3 and a 4. Might as well. Smaller numbers, okay? So I have a 2 delta B equals negative 3 delta D. And I know that delta B, okay, if I'm looking at delta B, it's going to come from PL over AE. So I have P, okay, P. I have the force that's in B, which I already told you was in compression in my mind. I'm assuming everything on this it's in compression. So I have negative force B, length B, area B, E of B, plus alpha, alpha delta T length B. Okay, and I know that delta D is, okay, what do I have here? Delta D, when I look at this little guy, I know that's going to be the force at D, the length of D, the area of D, and the E of D. And so I'm going to have to pull out another piece of paper here. Okay, and I'm going to re-summarize this. So I have that the force of D equals 50 minus 3FB over 2. And I have that delta B equals negative FB, LB, AB, EB plus alpha delta T, LB. And delta D is FD, LD, AD, ED. And we have this relationship of 2 delta B equals negative 3 delta D. So let's get these set up appropriately. So I have 2 times, okay, negative FB, LB, AB, EB plus, I'm just going to go back to my handy dandy little sheet that I made where I have everything kind of summarized. So I have alpha, I thought I had it summarized easy, 12.8 times 10 to the negative 6 per degree Fahrenheit. I have a negative 50, and I have LB. Equals negative 3, and I'm going to go ahead and pull these things out and put that inside a parenthesis. You'll see why in a minute. So I have negative LD over ADED FD. So it's still saying 3 times FDL, but I'm just isolating some things for just a brief moment. Okay, so now what I'm going to do is I'm going to note that I have an LB on both of these, and I'm going to bring that out. So I have 2 LB. Okay, I brought those LBs out, so I'm making these a little bit smaller. And now that I've isolated this, I can multiply by the reciprocal, and have an AD ED over 3 LD, and I'm going to bring that negative over just like that, and inside I have a negative FB AB EB plus 12.8 times 10 to the negative 6 times a negative 50 equals FD. Okay, and I know that FD is really 50 minus 3FB over 2. So this side is pretty simple. This is a giant pile of do. So I can go back in and add my numbers now. I have minus 2, and I have that LB is 60, area of D is 1, E of D was 29,000, divided by 3 times that length was 36, LD, okay, minus FB, I think it was 1.4375 and 10,600 if I'm remembering correctly, plus 12.8 times 10 to the negative 6 degree Fahrenheit times negative 50, okay, equals 50 minus 3FB over 2. So now I can simplify. I can actually look at this. I have a negative, so I can just make this a positive and a positive and a positive. So my negatives just magically went away. And I'm going to have 260 times 29,000 times divided by 3 divided by 36. I actually need 2 of these because I need to multiply it by this, and then I need to multiply it by this. So I'm starting my simplification here. 1.4375 divided by 10,600 divided by, and I get 2.114666 FB plus, okay, so I've got this one, and now I've got to simplify this out here with this. So I still have that 32,222 times 12.8, 10 to the negative 6, times 50. And remember, I've already pulled the negatives out. So, okay, so I get plus 20.622 equals 50 minus 3FB over 2. So I have FB on both sides and these numbers on both sides. So now I'm going to do my algebra. I'm going to bring this one over and subtract it, and bring this one over and add it. So I have 2.114. I can't read my numbers anymore. FB, okay, plus 3 halves FB equals 50 minus 20.622. So I can look at this side first, 50 minus, make that a negative, and add it to 50. and I get 29.378 on the right. Swap those back out, and I have 2.11 mess of a mess plus 1.5, so I get 3.61466 FB. And now to find FB, I can just divide through, and I have them in my stack. So I get that FB is 8.127, and I was using consistent units, kips, and it's positive. So I do have a tension member, just like I do have it's positive, which means it's going down in the direction I said, which means it is a compression member. Okay, I got a positive value. I assumed it to be in compression. And now I can go back and find FD. And remember, it is 50 minus 1.5 times FB. So I end up finding, okay, I have 50, enter. I'm going to swap those out. FB, so I'm going to have 3 times 2 divided by, and I'm going to subtract, and I get 37.8 kips. Okay, well, we need to really talk about these numbers that we got, okay? So I'm going to recognize that this was my aluminum, and this is my steel. And so after I calculate these, the next step, always, 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 is to make sure we didn't yield. So I know that for my aluminum, I think I wrote the yield stress somewhere, okay? For my aluminum, my yield stress is 60 KSI, okay? And that is greater than, okay, the force I got in B, which was 8.127 kips. That's great. When I look at my steel, my yield stress is 36 KSI, and that ends up being smaller than the force that I get in my system of 37.8 kips. That's a sad face. That's not how you make a sad face. That's a sad face. That looks like a little ghost from Pac-Man. Okay? So, I'm in a dilemma because my equations for delta and for delta for temperature, this right here, this PL over AE, this is assuming E, that I'm in that elastic region, that I am below 36 KSI, and I'm not. So what do I do with that? Well, unlike when it's by itself and it's free to just have all the deformation at once, and it could just stretch and stretch for miles and miles if it needed to, we're in a system. So it's like me and you and I, me and you. We are like Mike and Sully from Monsters, Inc. And we're playing tug-of-war against another team. And, you know, I kind of peter out at 36 KSI. Okay, once we get to 36 KSI, I am no longer helpful. I've gone to my yielding, and we really don't want yielding in the system. So I have to stop here. I can't take anymore. But Mike, look at that. Mike has plenty of room to add some more. Well, wait a minute. I have totally screwed this up because those are forces, not stresses. I have to actually calculate the forces. I mean the stresses. But bear with me. I am so sorry. If I knew how to edit, I would stop and go back. I'm not even paying attention to what I'm doing. I'm just so excited that I knew we were going to have yielding on this problem. I need to find stress, and stress is force over area. And some of you guys at home are like, oh my God, I was trying to tell you, but you couldn't hear me, okay? So my aluminum, my stress is 8.127 divided by, and I had that cross section of 1.4375. And so actually it even makes it even smaller. 1.4375 divided by 5.65 KSI. Look, next step, yield stress. We got to make sure we are under yield stress, and stress equals P over A. Okay, so I apologize for that confusion there. Here's my 60 KSI. Here's my yield stress. It's even smaller now when I'm looking at that aluminum. With the steel, this is where I got carried away. We said it was a 1 inch squared, so I knew that the stress was 37.8 KSI. which is still a sad face, okay? So let's go back to Mike and Sully and tug of war. I can't carry this. I can't carry, this is the most that I can carry is that 36 KSI. And because of that, Mike, he's going to have to, my partner in playing tug of war, he's going to have to like pick it up. He's going to have to carry the rest. So unfortunately, this is no longer a true story, okay? Because I'm causing yielding here. So I can see that, okay? I can see that my steel yields. And the most I can have is 36 KSI. I can't carry that 37 like I kept thinking I could. Okay, I can't carry that much. And so, sorry, I'm trying to find the thing so I can fix that. Okay, so I also know that stress is P over A. So the force in B I need like 12 more erasers because all I do is erase all day long. All day long. So that force in D, which is that steel cable, the most stress it can have is 36 KSI. Okay, that's the most stress it can have. And I know that the area was 1 inch squared. It gave it to me as a cable. So when I multiply this across, the force in D can only be 36 kips. That's it. Okay, not that other value we calculated. We have yielding, and it can only be 36 kips. So if force D can only be 36 kips, when I go back to force D equals 50 minus 3 force B over 2, then I'm having to limit this now to 36 kips. And when I do that, let's look and see what happens. Okay, I have 36. I have a 50 minus, okay, I have a negative on both sides, so I can get rid of it. 2 times 3 divided by, and I get that the force in B is now 9.33 kips. Okay, so my good friend Sully, who is playing tug of war with me, because I'm Mike and I'm playing with Sully, when we're doing this tug of war and we're pulling this way and the other team's pulling this way and we don't want the ribbon to cross the muddy water, okay, we don't want that to happen. I can't pull the 37 that the system is wanting me to pull. So I'm gonna have to knock it at 36. And when I knock it at 36, that means Mike has to increase what he's going to pull, that 9.33, and that is so that we so that I'm not yielding, because I don't want to yield, and we can still maintain that equilibrium in our system. Okay, so these are the real answers. This caused yielding, we found right here. So I have to decrease this force. And remember, you check your stress. Stress is force over area, 36 KSI. So divided by, I have over area. I can reduce this by 36 times that area, and I get that force in that cable is 36 kips. Okay. So if the force in B is 9.33 and the force in D is 36, I can now find the stress in B. And it's going to be the force in B divided by the area of B equals 9.33 kips divided by 1.4375 inches squared. And when I do that, I get 9.33, 1.4375 divided by. So I get 6.49 KSI. Okay, and that was higher. That was higher. Okay, that was higher than what I had when I had that smaller force. So my force had to go up, therefore my stress goes up. But I'm still less than 60 KSI. So we're good. Okay, we're good. And then that means the stress in D is at 36 KSI because I'm stopping at yielding. Okay, that's my yield stress. So now when I want to find deltas, when I go back to my relationship that I have from compatibility, and I go back and I have that delta A is to 4 as delta B is to 3 as negative delta D is to 2, okay? I can't use this one. I can't use this one because we are at 36 wanting to teeter over into that non-elastic behavior. And so I have to stick true with if we're using PL over AE, okay, then I need to stick with that PL over AE, because that's the one that the equation is actually valid for, okay? So, but we have to remember we also had that temperature change, okay? We had that temperature change. So when I look at delta A, we're going to move that 3 over. We have 4 times delta B equals 4 times. And now I need to get the force of B. B, length of B, area of B, E of B. Okay? Plus alpha delta T L. Okay? We need to have all of those things in here. And this time, okay, I get really wonky with things. I am probably not as consistent as I should be. I know that this force is in compression, and so it's going to make us want to move down. And I know that this temperature is decreasing, so I also know that that's going to make us want to go down. And both of these are going down just like point A is. So B is going down by both things, A is going down. So I'm just going to get rid of negatives. Just get rid of negatives, because I know that the compression and the change in temperature are causing that bar to get shorter. So I have delta A equals 4 over 3. Force of B, I have to use that new adjusted. And then I have a length of 60 inches. I have an area of 1.4375, 10,600. Plus 12.6 times 10, 12.8 times 10 to the negative 6 degree Fahrenheit times 50 times 60. And that is how we can actually go back and calculate that delta, the total delta of B. And so what I find is that delta A is 0.1002 inches down in the direction that I kind of assumed it would be. So there's my delta A. And then here are my answers for stresses. And we did our yield check. So I hope that kind of makes sense. And I'm sorry for the little, I was doing stress, but I forgot to do stress because I was so excited about yielding.